Ready?
Yeah.
Okay. Final lesson of the unit. We're going to be solving logarithmic equations today. And we're going to put all our tricks of laws of logarithms as well as some skills that we have in our back pocket from grade 11. We're going to be using that today. Okay, so there's two different things we need to know to solve logarithms. One is that we can introduce a logarithm on both sides, and if they have the same logarithm with the same base, then we can set the arguments equal to each other. Okay, so if we have a logarithm with the same base on both sides of the equation, one term equals another, then the arguments can be set equal. The other way is that we can change our logarithmic form into exponential form and then solve for an unknown. So those are the two skills that are going to help us. So let's check out what Alice has done. So Alice is solving the equation. Guys, are we ready? Thank you. Okay, so we have logarithm base 5, argument x plus 1, plus logarithm base 5, argument x minus 3, that equals 1. Alice has shown her work. First, what she did was she decided to take the product law. So this is our initial equation. From there, she noticed we had two logarithms with the same base, and they're adding. So if they're adding with the same logarithm base, we can multiply the two arguments. So now we have log base 5 with x plus 1 times x minus 3 as our argument, and 1 is still 1. Okay, then from there, she converted to exponential form. So she went 5 to the power of 1. Okay, 5 to the power of 1 equals the argument. And after that, we just have a quadratic equation that we need to solve. Okay, so we're going to FOIL and solve. So x times x squared. Then we get x times negative 3 is negative 3x, plus another x is negative 2x, minus 3 equals 5 to the power of 1, or just 5. Now hopefully we can recall from grade 11, if we have a quadratic equation, we need to first set it equal to 0. So let's move the 5 over. And how do we solve for x? We factor. So I need two numbers that multiply to negative 8 and add to negative 2. And we'll get x minus 4 times x plus 2. So from those two factors, we have our solution that x equals positive 4 and x equals negative 2. Okay, when we're solving logarithmic equations, it's very important that we verify our answers. Okay, we can't just assume that 4 and negative 2 are actually our answers. We might have extraneous solutions. So we're going to sub x equals 4 back into the original equation. We're going to check to see if left-hand side equals right-hand side. And then we're going to do the same with x equals negative 2. Okay, so if x equals 4, let's sub that into the original equation. And we get log base 5. 4 plus 1 plus log base 5, 4 minus 3. I need to check if that's going to equal 1. So log 5 to the 5, what does that equal? 1. Okay, if the argument and the base are the same, it equals 1. Okay, now we have log base 5 to argument 1. 5 to the power of what equals 1? 0. And you could plug that in your calculator to calculate to confirm if you wanted, but we can also do it in our head like we just did. Okay, left-hand side equals right-hand side. So that one works. Now we're going to check x equals negative 2. So again, subbing into the original equation, we have negative 2 plus 1 as our first argument. And then subbing into the second argument, we'll have negative 2 minus 3. That equals 1. Let's just simplify here. guys notice about the arguments? They're negative. I'm just going to remind you guys what a logarithm looks like. Okay, can we have negative logarithms? Does it exist over here? No, we can't have negative logarithms. So because these are negative, x is considered, or x equals -2 is considered extraneous. And one more time, that's because we cannot have negative arguments. Okay, we can't have negative bases, we can't have negative arguments. Anytime you have a logarithm with a negative base or argument, there's no solution to it. They don't exist. And if you don't believe me, you can just try and put in log -5 divided by log 5, and you'll see an error. Jackson didn't believe me, he's checking. No? Oh, okay. Okay, so it's very important to always verify your work because you might have extraneous solutions. Let's just try a few more examples. And before we try this next question, I just want to actually go to part B first. Can you guys put in your calculator, in your y1, log x squared? What you're going to notice is you get a graph that looks like this.
No. Yeah. No.
Let me check.
It just doesn't show any negative y.
Okay, so what's happening is with your window settings, you guys are getting it looks like this, right? Okay, you're just not zoomed in close enough to show that it's actually approaching the y-axis. It's not going to touch it. So you just got to change your window settings, and Jared's done it. Okay, he's getting a better picture. It still looks like it's touching, but you have to basically zoom in really, really close to show that it's approaching that line. It's not going to cross. If you, guys, why don't you go second table? And look when x equals 0. What do you guys see?
Error.
Error. That's because the graph is never going to touch x equals 0, which is your vertical asymptote. So what can we say the domain for this function is? How about we just make life easy and say x can equal 0? And it's everything else. Okay, how are we doing with that? Okay. We'll come back to this graph in a little bit. Alright, the next one, we're going to put in our y1 is equal to 2 log x. Do you guys remember what I just said about negative logarithms? Can I put in a negative value for a logarithm? No. So this graph is only going to exist on the right-hand side. And again, our vertical asymptote is still x equals 0. But what's our domain this time? X is greater than 0, good. So we have two very different graphs, and the reason why we can have negative values in this one, and we can't in this one, let's say I plugged in x equals -5. -5 squared is positive 25, so it works out. Okay, but if I put that same -5 into here, we're not allowed to have a negative logarithm. So even though by the power law, we can say that log x squared is equivalent to 2 log x, their graphs are very different. And we learned that from lesson 8. Okay, that was the very last lesson of lesson 8, the very last page of lesson 8. So let's go ahead and solve these, and we'll see which solutions are possible, and we're going to use our graphs to help us a little bit. So we have a logarithm on both sides, base 10. Just like we can add logarithms to both sides, we can remove logarithms from both sides. And we can say that the arguments are equal. We have x squared equals 16. To solve for x, we just need to square root both sides, and we need to remember to take the positive and negative square root. So x equals positive or negative 4. Then we need to check or verify. Okay, let's check for x equals positive 4 to start. So we're going to sub into the original equation, log 4 squared. Will that be equal to log 16? Okay, does log 16 equal log 16? Yeah. That's going to be the same. Now let's sub in negative 4. Okay, log negative 4 squared. Does that equal log 16? Yes, log 16 equals log 16. So when you're verifying, you're always proving that the left-hand side of the equation equals the right-hand side. So I'm going to introduce a little bit prematurely, but why not? You guys, could you put this back into your y1, so log x squared. And we're going to put into y2, the right-hand side of the equation, log 16. And it's going to be a value that's going to go across as a line. The solution are the intersection points between these two graphs. So you're going to go second trace, number 5 for intersect. And you're going to figure out what are the x coordinates for those intersection points. One solution will be at positive 4, and the other one will be at negative 4. So graphically, we can also solve this question by using the intersection method. Does anyone want me to show that on the calculator, or you guys are good with that? Pardon? You need some help? Oh, press enter. Now it should load. But you'll probably only go to 6 higher standard window settings. Now you'll be able to solve. No problem. Okay, so we have two solutions, positive 4, negative 4. Now let's go on to the second example. 2 logarithm x equals log 16. So pretty much we can solve this the exact same way using the power law. Okay, the 2 out front can be moved as an exponent using the power law. And then we can set them equal to each other. And the answer is, again, positive negative 4. The only difference is how we verify. Yeah? No, go ahead.
But like when you do it like on your graph, it's
Right. So how you solve for the values doesn't matter, but when you check it, you have to put it back into the original equation.
Okay.
Yeah. Okay, so we get x equals positive negative 4 again. Now we just have to check. So if we checked x equals 4, we would get 2 times log 4, and just calculate, does that equal the same thing as log 16? What's the value of log 16? 1.204. One 19983. Okay, and then when I go 2 times log 4, I get the same thing. 1.2041, yada yada yada. Okay, left hand side equals right hand side. So x equals 4 is the solution. And I'll talk about the graphing method in one moment. Okay, let's check x equals negative 4. 2 times log of negative 4, will that equal log 16? Okay, can we calculate a negative logarithm? Nope, so we're going to get an error. So this is extraneous. So then that concludes that our only solution is x equals positive 4. And let's take a look at the graph now. Do we have any negative x values? So just by understanding the graph of 2 log x, if you get a negative value, first of all, you could just look negative, plug it in, it's going to be a negative logarithm, so you should know. But graphically, it doesn't exist over here, so x can't be negative. What we're going to do is plug into y2 log 16. You should already have that into your calculator. You're just going to change y1, not y1 to 2 log x. And your log 16 will be a value that will intersect the graph at one point. Can you guess what the x value will be? 4. And if you're not sure, second trace number 5 for intersect. And I think we've probably answered part C pretty well. The reason why there are 2 answers for log x squared compared to 1 answer for 2 log x is because of the domain restrictions. And this one we only have an asymptote in the middle, but the graph exists to the left of that asymptote and to the right. Okay, and so we can have positive or negative, just not 0. Whereas here the graph exists only to the right of the x-axis. So it can only be positive. So now we're going to get creative using our power law, our quotient law, and our product law to solve logarithmic equations. And we're going to use our skills from Math 20 on how to solve quadratic equations. Okay. So I have 2 logarithms on the left-hand side of the equation, both base 4. We're subtracting them. Which law can I use? Quotient law, good. Okay, so I now have log base 4 of x plus 1 divided by the second argument, 2x minus 3. That equals log base 4, 8. Would you guys agree that I have a term equals another term? And would you agree that the logarithm has the same base on both sides? Oh, perfect. No disagreements. So I can cancel out the logarithms, and I'm left with just the arguments. I have x plus 1 divided by 2x minus 3 equals positive 8. Now I can just solve for x. So multiply the 2x minus 3 on both sides. That's going to cancel out the denominator. Whatever you do to one side, you have to do to the other. And I get x plus 1 equals 8 times 2x minus 3. And I just expand. And lastly, we're going to solve for x. So let's subtract x from the right-hand side to the left-hand side. We get 15x. We're going to add 24 to the left side, so 1 plus 24 is 25. To isolate x, divide by 15. And then we need to reduce. Both the numerator and denominator have a factor of 5, so we can cancel that out. and we get 5/3. How will I check my answer? Plug it back into where? The original equation. And I'm just going to be generous on this one. If you did check your work, you would see that the left-hand side does equal the right-hand side. We've checked a few now, so I'm not going to verify all of them with you, but if that was a test or an assignment that you guys were doing independently, you always want to check. But I've verified it for you, okay? Don't worry about it. Alright, the next one is very similar. Okay, how could I get the logarithms with the same base to the same side? Yeah, this is actually, we're subtracting this logarithm, so to get it to the other side, we're going to have to add. We have logarithm base 6, x plus 4, plus logarithm base 6, x plus 3, equals 1. Jared, which law do you fancy?
Product law.
Product law, perfect. So we're going to apply the product law, where we multiply the arguments of each logarithm. And if I don't have that a logarithm of the same base equals a logarithm of the same base, I have to use the exponential form. Okay, so we're just going to convert this to exponential form now. So I get 6 to the power of 1 equals my argument x plus 4 times x plus 3. Then let's expand by foiling. We get x squared, 3x plus 4x is 12x, 7x, sorry, and 4 times 3 is 12. That's where the 12 came from. Set your equation equal to 0, so we're going to subtract 6 on both sides. We get x squared plus 7x plus 6. Can we factor it?
Yeah.
Yep. X plus 6, x plus 1 gives me, when I multiply 6 times 1, I get 6, and when I add 6 plus 1, I get 7. So we have two solutions. X equals negative 6, and x equals negative 1. Let's see which ones are true. If I plug negative 6 into this first argument, I result in a negative argument. Is that possible? No. So when you plug in x equals negative 6 into just one of the logarithms, you're already seeing that it's not possible, because you can't evaluate a negative logarithm. So this solution is extraneous. What about if we put negative 1 in? Do we still get a positive? Do we still get a positive? So we're quite positive that this might be a solution, but you still have to sub it in. Yes, it's cheesy. You still have to sub it in to see if left-hand side equals right-hand side. So I'm going to let you guys do that. I'll just show the work below. So log base 6, subbing in negative 1 for x, we get negative 1 plus 4 equals 1 minus log base 6, negative 1 plus 3. And just remember, we're subbing into the original equation. So just cleaning things up, we get log base 6 of positive 3 equals 1 minus log base 6 of positive 2. So to calculate this, we'd have to go log 3 divided by log 6 equals 1 minus log 2 over log 6.
Can those logs can't cancel?
No, because we have this term that doesn't have a logarithm on it.
Oh, okay.
So if you guys calculate that, let's just see what the left-hand side is. We get log 3 divided by log 6, 0.613. Okay, and then when I calculate on the right-hand side, again, we get 0.613. So if right-hand side equals left-hand side, we found ourselves a solution. So x equals -1. It does not equal -6. So did anyone attempt to do number 1 on their portfolio yet? What we're learning today is how to solve number 1. So if you solved it, good job. Okay, next one. Let's think of all the laws of logs and see how we're going to solve this. Because I have this coefficient out front, can I use the quotient law yet? No, so let's get rid of that too. Which law do I use? Power law. What did you say? Okay, power law. We're going to move that 2 from the position of a coefficient to the position of an exponent. And in one step, is it okay as well if I move that -3 to the right-hand side as +3? Too bad, doing it anyways. But if you don't understand where that came from, it was -3 and I've just added it to both sides. Now I have a logarithm with the same base. We're subtracting them, so now we can use the quotient law. So log base 3 of x squared divided by x plus 3, and that equals +3. And because there is only one logarithm, my strategy is to put it into exponential form. So 3 to the power of 3 will equal x squared divided by x plus 3. The base of the logarithm is always the base of the exponent. Okay, the base of the logarithm, base of the exponent. So let's just expand this. We get 27, 3 cubed is 27. That equals x squared divided by x plus 3. We want to get that x plus 3 out of the denominator, so we're going to multiply it on both sides. And we end up with 27 times x plus 3 equals x squared. Next, let's expand. So we're going to distribute the 27 to both terms, and we get 27x plus 81 equals x squared. We're back to grade 11. We have a quadratic equation. We need to solve for x. So set the equation equal to 0. I'm going to move everything to the right-hand side by subtracting both terms. So we get x squared minus 27x minus 81. I just moved both terms to the right-hand side. Can you guys brainstorm two numbers that multiply to negative 81 and add to negative 27? You might have to play around a little bit. But if you get tired of that, then you can use your quadratic formula, where x is equal to negative b plus or minus the square root of b squared minus 4ac over 2a. So let's just note, based on the equation we have, what our a is. A is equal to 1, so there's an imaginary 1 there. Our B is negative 27, and our C is negative 81. So we just have to plug that into the equation. So we get negative 27 plus or minus the square root of negative 27 squared minus 4 times 1 times 81, negative 81, divided by 2 times our A, which is 1. And keep in mind there's a plus and minus, which means there's 2 answers. So if you guys could, please calculate your answers to 2 decimal places. Anyone calculate a solution? Not yet? Anyone need help calculating a solution? Do you have some awesome math apps on that phone? You've been on it for a while. There you go as well. In your head? You get 324 or whatever 27 squared minus 2. What are you doing? Oh, you're trying to factor still? Just so you know, it's not possible. And that's why we're using the quadratic formula. Oh, okay. So my advice to you is if you are trying to figure out 2 numbers that multiply to your C, or your AC, and add to your B, and you're taking ages to come up with those numbers, automatically use your quadratic formula. Okay? And in this case, there actually aren't 2 numbers that do that, so that's why we're using the quadratic formula. What did you get?
29 point, like plus 29.27. 27.
27? Yeah?
You're kidding. Oh no, 7.2, yeah.
Okay, good. And did anyone get the second solution? The negative one?
2.72.
Negative 2.72. Good. Okay, so these are the 2 solutions you should have calculated. And I just want you to look at the original equation and tell me just by inspection, just by looking at it, which one is extraneous.
Negative.
Negative, because if you sub that negative number back into a log x, log of a negative does not exist, so this one's extraneous. And I'm just going to give you guys a little help again. I've already verified 29.72 with all the decimals back into the original equation, and this one does verify. Okay, you always need to verify. I'm just saving us a bit of time right now, okay? Now for the complex ones, but actually they're not that complex. They're not too bad, don't worry. Alright, so to solve a question like this, where we have a logarithm with a base to an argument that also has a logarithm, what we have to do is we have to convert 2 times into exponential form. Okay, so looking at this logarithm to start, we have our base 2 to the power of 1 equals your argument. So let's first convert. 2 to the power of 1 equals our argument. Log base x, 3x plus 4. Still a logarithm, so I get to convert again to exponential form. Hey, what's my base? What's your exponent? 2, and your argument, 3x plus 4. And again, we have a quadratic equation. Just move everything to one side and we get to solve. So x squared, we're going to subtract 3x, and we're going to subtract 4, and that equals 0. Two numbers that multiply to negative 4 and add to negative 3, get x minus 4, x plus 1. Where you at, Bruce?
What do we do with that 2 up
This?
there? No.
This.
Yeah, 2 to the power 1.
So x to the power of 2,
Yeah.
x to the power of 2.
Okay.
So that's where the 2 is.
Gotcha.
Okay, and the reason why I didn't put this 1 because Bruce, 2 to the power of 1 is just 2. So from our first factor we get x equals 4, and from our second factor we get x equals negative 1. And remember, we always need to check for those extraneous roots. Why don't you guys practice? Okay, I'll give you a minute to practice checking.
Yeah.
Who was just yawning? That was a big yawn.
Yeah, but they both could never do
Just type it into the quadratic.
it.
Just type it as a quadratic equation.
Hey, log with base 4, argument 16. That should equal 2 because 4 to the power of 2 equals 16. What can we say when our base and argument are the same? It equals 1. So left hand side equals right hand side. And we're going to sub in x equals negative 1. And let's just clean things up and I'll just talk about something in 1 second. Can you guys try to calculate for me log 1 divided by log negative 1? Is it possible?
No.
No. Okay, so because there's an error, we say that x equals negative 1 is extraneous. How are we doing so far? Our complex one's not bad? Okay, this first part, part A, it's pretty much review. So I want you guys to see if you can use your laws of logs for part A only to solve this equation. Hint, one of them has a coefficient, one of them doesn't. So you want to make sure they're in the same form before you do anything. Hint, you're going to use the power law on one of the logs. The way you choose does not matter. Stan, do you want to use the power law on the first term or the second term? Doesn't matter. First? Okay. So Stan wants to apply the power law to this exponent 2. So that means we can put the 2 out front. If you chose the other way, keep going with it. It's fine. It will work out to the exact same thing. Okay, we have a log x and a log x. They're the exact same thing, so we just have to add together the coefficients. 2 minus 3, we get negative 1 log x. That equals 10. So 2 minus 3 is negative 1. Then I'm going to divide both sides by negative 1. And I get log x equals negative 10. It's base 10, so I can convert to exponential form, and I get 10 to the power of negative 10 equals x. Or I could have written that as 1 over 10 to the power of 10. Who did it the other way? Anyone? Okay, I'll just run through that quick. So if we had log x squared minus, in this case using the 3 and putting that up as an exponent, I would get log x cubed. That all equals 10. With the same base, so we can apply the quotient law, we get log x squared over x cubed. That equals 10. And then apply the exponent law. 10 to the power of 10 equals my argument, which is x squared over x cubed. That works out to be 1 over x. Okay, flipping the position of these, we actually get that x equals 1 over 10 to the power of 10, which is exactly the same. So either way, you would get 1 over 10 to the power of 10. And don't forget to verify. We're not going to verify this time, but don't forget, always verify. So for part B, this is a good question. How come solving this question is not the same as solving part A? What's the difference? Good, there's a set of brackets around this logarithm x, whereas here, we didn't have it. Hey, if we look at this term here, that's like saying log x times log x. You can't move that exponent out front magically because it's the entire log squared. Whereas up here, the exponent was just on the argument, and that's why we're allowed to move it out front. Not in this case. It's two separate logarithms that's multiplied by itself. So we can conclude that log x squared does not equal log x all squared. So what happens if we get a question that's like part B and we have to solve? Well, using the steps below, that's how we're going to solve it. Okay, so first what you need to do, let's just rewrite what the question is. We have log x all squared minus 3 log x. That equals 10. Our first step is we're going to replace any log x with a letter. Okay, so step 1, replace your logarithm x with a new variable. In this case, they've chosen a. So if I sub a in, I get a squared minus 3a, and that equals 10. Does that just look like a regular quadratic equation to solve now? Yep, so we set it equal to 0, and we get a squared minus 3a minus 10 equals 0. After, as usual, we need two numbers that multiply to negative 10 and add to negative 3. We get a minus 5, a plus 2. Now, do we have anyone out there whose first instinct is to say that your answer is positive 5 and negative 2? Some of you might, but you have to remember that a is not actually a is log x. So we have to sub log x back in before we solve. Now we can set each factor or each binomial equal to 0 to solve. So let's do the log x minus 5 equals 0 to start. We can add 5 to both sides and we get log x equals positive 5. Convert to exponential form and we get 10 to the power of 5 equals x. So we've solved for one solution. And now we need to solve for the other one. So looking at the second factor, log x plus 2, we're going to set that equal to 0. Isolate the log x by subtracting 2. And then convert to exponential form, we get 10 to the power of negative 2 equals x. And if you wanted to write it as 1 over 100, you could as well. And if you wanted to expand 10 to the power of 5, that's fine too. Okay, last step, do not forget to check your solutions for extraneous solutions. And when we check these ones, we'll just help you out. They both work out. And that's that. Exponents and logarithms. Done.